Welcome to week 5 of Math 320. The goal of this week is to discuss the monotone convergence theorem and Cauchy's criterion for convergence. In between, in order to understand Cauchy's criterion, we will take a first look at the concepts of the lim sup and lim inf of a sequence. We will return to more discussion of the lim sup and lim inf in a later week, limiting ourselves this week only to that which we need to address the issue of Cauchy's criterion. The motivating question for this week is, can we prove that a sequence converges without already knowing what it converges to? You may wonder, why is this even a question worth asking? Let's start by returning to the definitions. First, we were told that a sequence converges if it has a limit. Next, we were told that a sequence has a limit y if we can prove it converges to y. Sort of circular, but okay. The phrase in quotes, that we can prove x sub n converges to y, is supposed to be replaced by the epsilon n definition, that for any epsilon bigger than 0, there is an index capital N, such that for any index beyond it, our sequence differs from y by no more than epsilon. This gives a technical meaning to what it means for the sequence to converge to y. It, however, doesn't tell us how we can locate the limit, starting just with a sequence. In last week's lectures and exercises, you were asked to practice with a bunch of explicit numeric sequences, given by nice formulas. You are asked to use what you learned in calculus and college algebra to divine what a limit should be, and then prove that that is the limit. But hopefully you notice that those are very special cases. We mentioned in the first lecture last week that sequences can frequently be given by something other than explicit formulae. In these cases, if we don't have an easy way of computing the values of the sequences, how can we prove that a sequence converges if we don't know how to guess its limiting value? You may say, okay, let's just use a computer to compute many terms of the sequence and see if it settles down, and then guess based on that. But the whole point of sequences is that what happens eventually, as n goes to infinity, is supposed to be independent of what happens in any of the first however many finite terms. From the perspective of computations, to have the confidence that we can just compute a large number of terms and get an approximation of what the limit should be is presuming that the sequence actually converges. But to prove that a sequence actually converges, you need to know what the limit is, and this is a chicken and egg problem. Since we have some number of students studying computational math in this course, where computers excel in science engineering is the ability to perform approximate evaluations of complicated mathematical expressions. For this to actually work, we need some theoretical guarantee that the algorithm used will actually output a good approximate solution. Quite frequently, the algorithm can be regarded as computing the value of x sub n for some n very large of a sequence that converges to the desired solution. The theoretical guarantee that the algorithm works for large enough n is precisely a proof of convergence of this sequence. So this is why understanding sequences and their convergences, absent knowing what the limit is so important in mathematical analysis. Our goal this week is to present the two most important ways of resolving this difficulty. They are the monotone convergence theorem and Cauchy's criterion for convergence. These two theorems allow us to assert that a sequence converges without knowing a priori what the limit is. To do so, we have to pay a small price. The price that we need to pay, however, comes for free because we are working with the real numbers. It turns out that both of these theorems run on the order completeness of the real numbers. This is one reason why we like to work with the real numbers. Without its completeness, it will be much harder to assert that a sequence converges without already knowing what it should converge to. Cauchy's criterion, in particular, is what is hidden behind all the series, not sequences, series convergence tests that you learned about in Calculus 2. Time permitting this semester, I may show you a few examples on how this works around week 7 or 8. Before discussing Cauchy's criterion, however, it is useful to introduce the concepts of the lim sup and lim inf. These concepts make it easier to organize the arguments used. We will explore these concepts in more detail in a later week.